Now, after the clarification of the argument passing semantics, let's look into the flow functions again. First of all, the call flow. So, consider you want to analyze this method foo here that is called at this statement. So, of course, you will propagate the zero flow fact first. Then, as A is passed into foo, you will also propagate from A to F. Now, let's assume B is a local variable of the calling context here. So B is not propagated to foo, and hence we do not draw anything in the call flow to the context of foo. And now let's further assume that G is a global variable or static field. And as it is a global variable or static field, it's also visible in the context of foo. And hence we also have to propagate it to the context of foo. Now let's look into the return flow. And by the way, the call flow, so what we've discussed before, applies to Java and C and C++. So there was no difference in handling, but we will see the differences later on. So now let's discuss the return flow. So we have this parameter f here, which is an int. So we know there is no back propagation of f to a. So while we do draw this this data flow edge here for the zero flow fact again, we do not back propagate f to the context of to the calling context here. So there's no outgoing edge for f. But as we return the value s here, we will propagate s to r. That is for sure. And also, considering again that G is a global variable or a static field, we will also back propagate it back to the calling context. So we will also draw this flow function here. Now let's get to the differences. So now let's consider this code here is Java, and just for a quick reminder what the semantics are. So we have a reference value f here. So f is a reference to this object here. So f itself is not backpropagated, but all the fields of f are backpropagated. So how does it look like in return flow functions then? So first of all, again, those flows here that we've discussed on the slide before. But there is no flow still from F to A. But there is a flow for all of the fields of F that we might encounter here inside of the context of foo. And those will have to propagate it to the respective field of A. Alright, now let's discuss it for C and C++, and there are even some more things to consider here. First of all, again, we have those flow functions here that are discussed, or that were discussed before, so there's nothing special here again. And yeah, so what do we have here? We have call by value, so f itself is not backpropagated, but the transitively reachable fields here by definitely reference here, right? So the flat fields here of this object here, A, so the 42, so if anything happened to this integer field here, it would not be backpropagated, but what we have here in the object O, that would be backpropagated, and this case distinction really is made here. So this fact here denotes the flat fields, so that would be, for example, the 42 here. And this one here is actually any dereference of a field here, right? So that would be, for example, like this here. So we do not have a flow function for this one here, but we do have a return flow for this data flow fact here. And of course, I mean, this kind of collapses all of the fields. It could be many more fields here, right? But just for the presentation here, I collapse those fields together. And also, just to prevent confusion, this operator here, so this is the dereference operator, and this is considered to be the asterisk, like mentioning it's all fields. But because both notions are quite common, so both this for dereference and also this as denoting any fields, I decided to keep it like this and hoping that this would be the least possible confusion here. Alright, what does it look like when we have call by pointer? Well, again, for the zero flow fact for S and for G, nothing changes. But now the dereference of F is then also visible in the calling context here, so we will have to draw this flow here from dereference of F to dereference of A itself, so that's referring to the base. And also any fields that are reachable from that base here, right? So that would be, for example, so the base would be basically the object here itself, and this would refer to any fields that we see here and also possible transitive fields in further dereferences or further access paths here. And also for those we will draw this flow function here. Now, the call to return flow, and this is actually the one where we have to take most care of, because let's consider again. So here in the dotted lines we see here the call flow, and here we see the return flow. And now obviously our data flow facts need to propagate somewhere. So it would be in most cases it would be unsound actually to kill some fact here just by forgetting to draw one or to propagate those facts here, right? Here, for example, you will want to perform the propagation for the zero flow fact as well. And also you will want to propagate A here, right? Because it is it does flow into the context of foo, but it does not flow outside of the context of foo. And also here in the calling context, by definition, A is not modified, so we absolutely need to propagate it over this call set here. So we will definitely have this call to return flow for A as well. Now, R is the return value, and as it is set by this statement here, it is would be killed here. Even if we had some propagation here before, we would actually kill this value here. So we are not drawing this data flow edge here. And as we propagate the parameter, actually not the parameter, the global variable G, both into the context of foo and out of it, we are not drawing this call to return flow for G either. Now, what does the call to return flow then look like for Java when we do call by value and have a reference value? So here again you see the call flows and the return flows that we've discussed before, and now we have to draw the call to return flow edges here. So again we have to propagate the zero flow fact as we always do, And then yeah, R obviously is killed here, so we are not having a call to return flow here. And G is propagated through foo, so there is no call to return flow either. Also for A dot star, so for any fields of A, we don't have the call to return flow here, because they all go through the context of foo. But for A, we do have this propagation here, as A cannot be modified in the context of foo. Alright, what does the call to return flow look like then for C and C++ when we do call by value with a compound type argument? Again, F is not back propagated to A, so whatever is done here, A itself has to get this call to return flow here. But first, of course, we have the zero flow value, zero flow function that we will get here, so the call to return flow for the zero flow fact. Then, as I just said, for A as well, then R is killed, G is propagated through foo, nothing interesting here. And actually, these are transitively dereferenced field here. They also go through the context here, but the flat fields of A, like for example the 42 here, so flows into the context of foo, but does not flow out of it. So for that one, we will also need a call to return flow. Actually, it's here. So we will need a call to return flow here for the flat fields of A. Alright, and now finally the case with call to pointer. Again, we have the zero flow fact that we have to propagate through. So not propagate through, propagate over the function call of foo. And still A cannot be modified by this function call, so we will have a call to return flow for A. R is the return value, is killed, G flows through foo, and the dereference of A also flows through foo, and also the transitive fields also flow through foo, so we don't have any further call to return flows here in this case. Now you might wonder why it even matters to be so careful and distinguish so many different cases when it comes to call flow and return flow and call to return flow functions. And this is why. Assume you have an incoming data flow fact and you have some incoming edge function on that flow fact. And then what you do is you have a call flow function and propagate the call flow, and on the edge here nothing interesting really happens, but then in the called function some data flow effect on the edge domain takes place. So you have this edge function eSummary here, and now you have the return flow function, but you also have some flow function and edge function as well that is a call to return flow for this very fact that you came in here. So now what is happening in this case here? The on-the-fly algorithm will compute the resulting edge function at this point here, and what it will do is basically this one here. It will follow this flow here and then follow this flow here and merge it together. And the result of this merge, after we simplified it, is this one here. So what does it mean here? It roughly means that it performs a merge of both edge functions, so both ways here. So it will take into account the effect of this summary edge function here, and at the same time it will not take it into account. So for example, if you remember this tiny little code example we had at the very beginning, if this would be the inc function and you would do an increment here, then eSummary would be here a +1, and this call to return flow would be just identity flow. So we would merge both applying the effect and not applying the effect together. And depending on your lattice in the edge domain, this can actually quite quickly over approximate even to top. So that would mean you don't have, for example, in the constant analysis, you wouldn't have a constant value anymore. So you absolutely want to avoid such over approximation wherever possible, and this is actually something that will render your analysis results useless very, very quickly if you do not take care of this particular aspect here, because as soon as you encounter a function call with some non-identity summary flow, this will definitely kick in, and this is something you want to avoid. But on the other hand, you cannot always avoid it. You've seen before that on the slides I showed you, I was referring to some fields and stuff, and if for example your analysis is not field sensitive or not field sensitive enough to distinguish those fields, then you will have to merge those facts together, and then indeed you will have to draw all of those edges here basically to be evened out with your analysis. So this is also something that you should keep in mind. Only if you don't want, if you don't want this over approximation here, that's a good thing, obviously. But at the same time, you always need to be sound in your analysis to be useful for any purpose. So you will definitely have to also draw those flows here, although that would mean the over approximation, but at least it's a sound over approximation. Now let's discuss special summaries. Assume you have a function where you already know the data flow effects, so both flow and edge effects of, and you don't really want or need to analyze this function anymore. So what you would do then is the following. You would not have those call and return flows. So you would kill, the call and return flow function, or you wouldn't even have called the return flow function, but the call flow function, so all call flows are killed. And instead, you propagate all of your facts in a call to return flow or a summary flow alongside the callee, and give it the edge function of the summary you are aware of. In PhASAR, you even have two ways to do this. One is, as I just said, kill the call flow function, so provide kill all in the call flow function, and introduce the call to return flow that summarizes the function. And the second variant is actually a more convenient one, where you provide a summary flow function really for such function calls to functions you want to treat specially, and for them you can provide a special summary flow function, and then the solver, if it recognizes that you provided a summary flow functions, it wouldn't even request your analysis to provide the call flow and call to return flow function. So yeah, this is just a convenient shortcut that we have introduced into PhASAR. Okay, speaking of which, it's time to get practical again. Let's see some examples for practical flow function implementations. So You've seen this one here before, at least the documentation part. So just a quick reminder. We had this ALOCA statement here, and we wanted to generate the left-hand side of the ALOCA statement from the zero flow fact. So what we do here is, so we are in the function get normal flow function, and first of all we do the case distinction of the statement, and here we perform a dynamic cast of the instructions of the current statement to ALOCA ins, which is the LLVM type for an ALOCA instruction, as the name directly says. So if this dynamic cast succeeds here, so then this expression here will be different from the null pointer, and we would enter this branch here. And then what you see here is a local struct definition, and this is a struct that inherits from the flow function type with this template parameter here. So this essentially just describes the type of the flow fact, and as our analysis domain parameter d_t, which denotes the flow fact, is const LLVM value pointer. Also, we have to inherit here from flow function with this template parameter here. So, what do we have here in this structure? We are getting passed some parameters here, both the value we have to generate and the zero value. And then we have a constructor definition, destructor definition. Not so interesting here, but what is interesting is the compute targets function. And the compute targets function will, as the name says, compute the targets. So basically will return the set of the facts that will hold after the statement with the incoming fact that is passed here in the source parameter. So here if the source is the zero value, then we generate the value gen that is passed here into this generate flow function. So that would be this case here, and the otherwise case. So if the source is not the zero value, so if it is some unrelated value, actually this edge is not drawn here, but it's trivial usually that it's just passing alongside. So then we will just return the source here. And then finally we return this flow function here. So we will instantiate this structure that we have defined here. And as you could imagine, there are actually many recurring patterns of flow functions that you might wanna come up with. And to account for this, we have actually prepared a lot of predefined flow functions inside of PhASAR that reflect this. And the very same flow function here could also be implemented using one of those predefined flow functions. And the implementation then would look like this. It's actually, you see, it's very much simplified here. So we still have this case distinction here for the statement, but now we are using one of the predefined flow functions here, and it's called gen. So this will just generate the fact here. We also have genIf and killIf and killAll and many more actually, so it's actually worth looking into the flow functions that we already have prepared for you. And with those it's actually quite convenient, and you very rarely really have to come up with your own custom flow function type and implement all those boilerplate stuff over there. Now, last but not least, let me show you some practical edge function implementations. First of all, a rather basic case. At the top here you see the signature of the getNormalEdge function interface method, and your analysis will have to implement this interface method and what is being passed here. So first of all, you see, you get the current statement and the current fact. So that would be the statement, so this would be the current statement here, and this would be the current fact. And then you get the successor statement, so that would be the statement that follows after here, and the successor node. So basically this will show you exactly the data flow function, so the data flow edge that was drawn here, and now your task is to associate an edge function to it. And here for this first case here, which is also nicely documented, as you should do as well, we have this edge here from 0 to 0, and it gets the identity edge function. And as most edge functions are actually identity flows, we provided this nice edge identity function here already in PhASAR, so you can just return an instance of this edge identity function here. Now, if you need to come up with a more sophisticated edge function, which is very likely that you have to if your analysis is doing something fancy, then it could look like this, and actually there are multiple steps that you will have to take. So first again, you will have to identify the case that you are referring to, and here for example you want to come up with an edge function for this alloca statement here that we discussed before in the flow functions, right? So you will want to check whether the solver is asking you indeed for the edge function of this particular edge. So you will want to check that the current node is the 0 value, so that's the incoming fact, and that the current statement is indeed an alloca instruction, and that the successor node, so the outgoing, so the target of this edge here, is actually the current statement. So if it's indeed the one that is generating A here, and not, for example, the one that flows from 0 to 0. Alright, and in that case, you again have this inline definition here of a struct that implements the edge function interface. Actually, the edge function interface is a bit is a bit bigger than the one that we had for the flow function. So what do you have to implement here? So first of all, you have to implement the compute target function here. And the compute target function will, as the name says, compute the target. So it will evaluate the edge functions, and it will return the computation result of this evaluation. As the edge function you're doing here is the bottom function, so you want to associate the bottom value with here, then obviously the compute target function here in this case is trivial, as you return the bottom element. If, for example, this would be an edge function for the addition, then you would so you could, for example, compute an addition operation here with maybe some other nested edge functions here that are below. And what you usually will have in the compute target method here, especially when you have some composed edge functions here, that you will actually delegate to those composed elements compute target function, and then work with the result. Alright, what further methods do you have to implement? And this is actually aligning to the concepts that we know about from the theoretical point of view in IDE, right? Because for the edge domain, you will have to define the composition of multiple edge functions, and here you implement how this composition is really done. So here, for example, you merge. So if not merge, you compose. So if you compose with bottom, you are still bottom. If you compose with identity, you are still yourself, and otherwise you delegate to to the other function to compose with. Now, just one point actually that keeps confusing everyone, including me, in PhASAR, and I believe actually also in Suit, bottom and top are just vice versa to what we called it conceptually in the lecture. So there's actually this is still something that's rather inconsistent and confusing. So here in the context of implementation, with bottom, we actually mean the most approximated value. So we are at the highest point in the lattice. So just to clarify that again. All right, and join with is the merge operator, and as this is the bottom edge function, we are still bottom because if we are at the top of the lattice, we cannot climb higher, basically. So no matter of what we are merging with, we are still bottom. So we just return ourselves. And then we have to define the equality operator. In this case here, it is rather straightforward because you just have to dynamically cast to bottom, and if the other edge function is also a bottom function, then this dynamic cast here will return a non-null pointer, and then and only then is it equal, and otherwise it's not. So this is how to implement the equal to for this particular edge function here. So, and yeah, with that, the implementation of the edge function structure is concluded, and then you just have to return an instance of this bottom edge function, and that is basically it. One final remark regarding edge functions is actually that the operators, so the compose and merge operators, should fulfill the conceptual properties that they have. So, for example, the merge operator should be commutative, right? So it should not depend on the order of which you merge two edge functions together. And this is also something that you should test during your development. All right, this concludes today's lecture and the final lecture of DECA I. I really hope you learned something practically usable in this lecture, and hopefully we will see you all again in DECA II. Stay tuned and goodbye.